entre 20 et 25 minutes. Lina? Ah non, c'est pas Lina. Quoi?
Hello.
Activé. Hello.
Hello. Ciao Alessandra. Ciao Sophie.
Hello.
Salut.
Mettre la vidéo.
How are you?
Good, and you?
I'm good too.
Ready to present?
Sorry.
Ready to present?
Let's say so. We have to. Are you ready?
Let's say so.
Okay, we're on the same boat then.
Yes, I think so.
Do we know how many people registered to the event?
I think Lina told me about 50.
50, I think.
Okay.
Yeah, more or less.
I think it was 40 something, and
Okay.
Lina is coming too, because she told me that she wants to test the.
Yeah, she have to check for broadcasting on YouTube.
Yes, right.
And we are waiting also one person from ISRM, Ricardo,
Okay.
to check if everything works, and then we can start the meeting, the webinar.
It's only 2 people. We are only presenting, both of us.
Yeah.
I think so.
Yeah, there will be an introduction from Lina that she presented the idea of this webinar, this monthly webinar, and the rule of the webinar itself. And then there will be your 2 presentations. So you have 20 minutes, and after each presentation there will be the question and answer. So firstly yours, Sophie, and then there will be the speech of Alessandra and the question and answer session of Alessandra.
Hi,
Ciao,
how
Lina.
are you?
Okay. Hey.
Ready?
Ready.
Yes.
Let's hope so.
Okay, perfect. Have you tried the share of the screen, or
No, should I try?
it could be?
Okay, I'm sharing. I can. I have the.
Oh, wait, I will give you.
I think I'm.
There we go. It's okay. Well, welcome to the kickoff session of the ISRM Young Members Seminar Series. My name is Lina Maria Guayacan. I am the Young Members Group Coordinator of the French Society for Rock Mechanics. With me, Federico Bagnon, Youth Representative of the Italian Society for Rock Mechanics. It is a great pleasure for us to be here today. Thank you for attending this first session. Before starting, we would like to thank support from International Society of Rock Mechanics and Rock Engineering mainly of ISRM Young Members Committee represented by Septa Decoda. We also would like to thank youth representatives of national groups that have joined this initiative from Spain, Australia, New Zealand, Japan, Chile, Canada, between others. Finally, we would like to thank Sophie Jung and Alessandra Insana for agreeing to present their works in this session. Now we will take a few minutes to present key information about the seminar. This project attempts to promote youth community interested in rock mechanics, engineers, research scientists, students, to foster knowledge in rock mechanics among this community, to share experience in both the industry and the academia, and to strengthen relations between different countries. We would like to invite different young members to participate in this seminar. The criteria for the speakers are be an ISRM member, have a maximum of 35 years or 40 years if a PhD degree was obtained in the previous 5 years, and have worked in rock mechanics and rock engineering for a period no longer than 10 years. Nominations can be made by the nominee's national group or by some other person or organization acquainted with the nominee's work. Self-nominations are also accepted. These nominations are to be addressed to the ISRM Young Members Organizing Committee. In the screen, you can see our contact email. This webinar will be held every month. We invite you all to keep in touch. Now I will hand over to the seminar of the day. Each presentation will last 20 minutes and will be followed by 10 minutes of Q&A. For the smooth running of the seminar, please turn off your camera and microphone during the presentation. And if you have any questions, you can use chat and also the raise hand feature. Okay, let's move on. First speaker today is Sophie Jung, currently doing a PhD at Laboratoire Navier at École Nationale de Pont et Chaussée on modeling the long-term behavior of the fracture zone around deep drifts excavated in Calais-Oxfordian claystone. She has a master's degree in engineering from l'École des ingénieurs de la Ville de Paris. She did her final year internship between Laboratoire Navier and Penn State University on numerical analysis of flow back after hydraulic fracturing. Today, she will present a part of her PhD work. Sophie, the floor is yours.
Thank you. I will share my screen here. Okay, it's working. Can you hear me?
Yes.
Okay, nice. So, hello everybody. I am pleased to be here today and to present you a part of my work in the context of my PhD work on, as Lina already said, the modeling the time-dependent behavior of the fractured zone around underground storage structure in Calais-Oxfordian claystone. My work is financed and supervised by ANDRA, which is the French National Radioactive Waste Management Agency. And I am currently working at Laboratoire Navier under the supervision of Ahmad Pouya, Jean Sulem, Siavash Gabezlou, and Michel Borner. So my work is part of the project CIGEO. Nowadays, a great deal of the supplied energy comes from nuclear power plants. Thus, the treatment and isolation of the radioactive waste generated by activities based on nuclear energy have become fundamental concerns. France has identified the deep geological repository as a suitable and safe technique to conceive and implement deep disposal facilities for radioactive waste. You can see here, it is the project CIGEO located in East France in the deep geological formation of Calovo-Oxfordian claystone. And so here you have a representation of the future waste depository. And here in the right side of the slide, a map of the underground laboratory. So today the project is still tested through full-scale experiment embodied by the underground research laboratory, which consists of a network of drifts excavated with different techniques and subject to numerous in situ experiments. The field data mentioned in this presentation were measured on two drifts, so GED drift and GCS drift. I will always refer to the name of my, to the type of the drift that I will be working on as GED drift or GCS drift. The name is not very important, but just keep in mind that there are two types of drifts, and they are excavated in direction perpendicular. So during the excavation of the drifts constituting the underground laboratory, two different types of fractured zones have been observed, whether the drifts were excavated in the direction of the minor principal horizontal stress or in the direction of the major principal horizontal stress. So the first type of drifts here in this line, so you can see that the fracture zone tends to extend in the vertical direction of the drift, whereas in the second types of drifts, the fractured zone tends to develop in the horizontal direction. So you can see with that for the first kind of drift, the convergence are very different. So the vertical convergence are much higher than the horizontal convergence, whereas in the other types of drift, it's the horizontal convergence that are much higher than the vertical one. So having said that, it seems that the fractured zone influences in some extent the convergence of the drifts. So many research teams have been working on modeling the convergence of those drifts, and their work have been published. Some of the work have been published in an article by Saedi et al. In 2017. So the graph is kind of busy, but my point is, I will tend to make it clear. The graph shows different numerical simulation, hence the lot of curves. So convergence of GED drift in the vertical and horizontal direction. So here you have the in situ measurement of the horizontal, vertical convergence, and here of the horizontal convergence. So you can see that most models are isotropic, which prevents them from reproducing both vertical and horizontal convergence at the same time. So you can see here that in the numerical simulation, the both convergence are very similar, not like what is measured in reality, as just like that for this model. And so we can also name another model who is anisotropic, with the green curve here and the black curve here. So the convergence are better, are better represented, but the convergence rate is still not as measured in reality, since the anisotropy is only about the elastic and plastic part of the model. So hence, from that observation, I can present my two principal hypotheses for my PhD work. First, we consider that in order to simulate an anisotropic convergence rate, the model needs to include anisotropy in its viscous behavior. And based on the earlier in situ observation presented in the slide before, we assume that this anisotropy is mainly due to the fractured zone. So I will present you here quickly the outline of my presentation. So I have, as I told you, so what I'm going to present you is a part of my work, of my PhD work, and I told you my two principal hypotheses. So the first I will present you the first numerical simulation that I did of the convergences of GCS and GD drift with a continuous equivalent model with numerical calibration of the parameters of anisotropy. Then we will try to link the parameter of anisotropy to the behavior of the fracture, and so upgrade the numerical simulation. And finally, having linked the parameters of anisotropy to the behavior of a fracture, we will be willing to measure those parameters on a fracture. So we also developed an experimental setup, especially designed to investigate the creep slip of a fracture. So first, I'm going to present the model used in the numerical simulation. It's the model ANEL-VIP, which is already present in the FEM code DISROC, and it's a threefold anisotropic model. The elastic, plastic, and viscous part of constitutive law are transverse isotropic. The plastic and viscous anisotropy are managed by anisotropic stress scaling as introduced, but at the time only for plasticity by Hill in 1948. The anisotropy is defined by two plastic parameters and two creep parameters, two anisotropic creep parameters. So basically for anisotropic material, the parameters Fn and Ft are equal to 1, and the figure that are represented here would be a circle. Then if you change the value of Fn, you describe a change in the behavior in the direction perpendicular to the reference direction. So here you have one direction of reference, and by changing the value of Fn, you change the behavior in that direction. And so the circle becomes an ellipse, and Ft describes the behavior in shear. So the ellipse become a kind of star, which can be minimum or maximum at 45 degrees. Okay, so in our first model, we have considered one unique material for the whole medium, for instance, without making any difference between the fractured zone at the vicinity of the drifts and the sound rock. Our objective was to reproduce both measured convergence of GED and GCS drift with the same model. So you can see that, I tell you that the elastic, the plastic, and the viscous law and parameters are the same for both drifts. And the anisotropy of convergence, the anisotropy in the model are assumed to be due to the fracture. So we assume that the direction of anisotropy is the same direction than the main fracture around the drift. So basically for GCS drift, you have a vertical fracture, and hence transverse isotropic orientated in the vertical direction, and the anisotropy is rotated by 90 degrees for GED drift, as the fracture are orientated more in the horizontal direction. The parameters of the plastic and viscous anisotropy are defined by numerical calibration by comparison to the in situ observation. So as you can see here, in bold, you have the result of the numerical simulation, and the other curves represent a measurement of in situ vertical and horizontal convergence. There are many curves because many sections of the drifts were measured. And so the parameters of anisotropy are different between the two drifts, as the fracture density and orientation are not the same in both fractured zones. So while the convergence are well reproduced, the parameters of anisotropy are not clearly linked to the fractured yet. At least it's not easy to understand their physical or mechanical value. So since our idea is to consider that the observed anisotropic behavior is due to the fractures, we were wondering if we can properly link the behavior of the fractures to the parameters of anisotropy. So now the idea is to formulate with homogenization technique the elastoviscoplastic behavior of one representative elementary volume constituted by isotropic sound rock crossed by equidistant parallel fracture planes, and then describe the fracture zone by such REV. So you have here the case of GCS drift, and the REV is changed, the orientation and the fractures density is changed between the different zones. The whole medium is not modeled by one material anymore, but it's cut into different zones of different fractures density and orientation. This division into different zones is done based on statistics data obtained from all the drift excavated in the direction of the major principal horizontal stress. I will then refer to the simulation of these types of model simulation as a simulation of GCS types drift. So it's all the drift which present an horizontal fracture zone. Yes, so how does the REV behave? So for its elastic part, the behavior is of a classified stratified medium. Regarding the parameters of plastic anisotropy, so the parameters of plastic anisotropy is calibrated on the variation of the uniaxial compressive stress with regard to the fracture's orientation. And the parameters of viscous anisotropy is calibrated by homogenization technique used to express the macroscopic viscous strain tensor. The strength or the success in this calculus is that now we have a good understanding of the parameters of anisotropy, as they are a function of fractures parameter that are completely understandable and that we can actually measure through mechanical tests. So for instance, regarding the elastic part, the parameters that need to be measured are the tangent and normal stiffness of the fracture and the fracture density. So the stiffness can be measured through normal and a normal compressive stress and direct shear test. The plastic behavior is completely determined by the apparent cohesion and friction angle of the fracture. So this is also possible to determine them by direct shear test. And the last parameters that remain is the viscous displacement rate. And this is the more tricky part. It's not very clear what test to do to determine it, but that's also the point of my work to find out how to measure it. So now we have, of course, validated our homogenized parameters, our anisotropic parameters. So regarding the viscous anisotropic parameters, we have compared the behavior of an heterogeneous representative elementary volume to the continuous equivalent model. We have applied on both of the REV uniaxial compressive stress in both direction and pure shear stress. And you can see on the curves that the heterogeneous material and the continuous one are in good agreement with the parameters, with the anisotropic parameters presented before. So now I'm going to present very quickly the results on GCS types of drift. So the drifts which present an horizontal fractured zone. We have simulated the convergence of the drift with FEM code this rock with a model containing different zones of different REV presented before. So you have here 3 zones. I will go quickly. You can see that we can reproduce pretty well the convergency that are measured in situ. So I'm going to present now the experimental setup. So in order to study the creeping behavior of a fracture in the Calvo-Oxfordian claystone. So the experimental setup is designed to investigate the viscous behavior of a fracture in the Cox claystone, which comes to studying the slip of the interface between 2 blocks of the rock under constant shear stress. The blocks of Cox claystone are also kept under constant normal stress. The experimental setup is composed of a cylinder controlled by a lab view software that will dispense the shear force and of an odometric frame that you cannot see here, but that allows to apply a constant and stable in time stress normal to the fracture. So 3 rectangular blocks are cut in a core of Cox claystone. The dimension of the blocks are set on the diameter of the core provided by Andra. And from now on, I will refer to the 3 blocks as one sample. By shearing the central block between the 2 upper and lower blocks, which are blocked at their ends, so both blocks here are blocks there, and we push here. That allows us to avoid having to manage a contact between the rock and the frame. That's why we are shearing 3 blocks and not 2 blocks. 2 LVDT on each side of the sheared sample. So the middle one is the sheared sample, and 1 LVDT is placed. You can see it better here. 1 LVDT is measure the movement of the piston, and 1 other LVDT is placed behind the block. So yes, they measure the average displacement of the central block, and a force sensor is located here. Allow the piloting of the cylinder in constant stress. The middle block is 2 centimeters longer than the 2 other blocks, just to keep the sheared surface constant during the experiment. Moreover, in order to use digital image correlation, the lateral faces on each of the blocks, so you can see it here, are polished to bring out the microstructure of the rock and thus create a natural speckle. You can see here that the blocks are not polished, so it's quite a different aspect. And also the 4 surfaces sheared during the experiment are also polished so that the roughness of the faces is as similar as possible to the roughness of the sheared fracture present around the underground laboratory structure. Regarding the digital image correlation, we use a monochrome camera with 150 million pixel sensor, which is quite a lot, to acquire the images. To obtain a maximum resolution of the whole sample, the camera is mounted on 2 motorized displacement stages that you can see here. 1 stage is used to move in the direction parallel to the sample here. We take each time 2 pictures of the sample, 1 of the left side and 1 of the right side to increase the resolution of each picture. The other stage is piloted to make a very precise focus, so it allows the camera to move backward and forward to the sample. The focus of the sample is optimized by studying the variance of gray levels normalized by its mean value, and all of the process of focusing is completely automatized. So along the experiment, the automatic focus is run before taking a picture, and a picture is taken every 10 minutes, actually every 5 minutes, because 2 pictures are being taken. So why do we use digital image correlation, as it's not that easy to implement? It's because, as you can see it on the left side of the slide, the data given by the LVDT gives only the average displacement or deformation of the central block. So you see that there are more movement where we are pushing than on the other side, but it's because it's certainly because we are measuring with those LVDT both the behavior of the rock matrix and the behavior of the fracture, and only with those information it's very hard, I think maybe impossible, to separate the behavior of the fracture from the behavior of the rock matrix. This is why we use digital image correlation, because as you can see on the right side of the slide, with the digital image correlation, we have an access to the whole fracture and what happens along the fracture. So here you can see on the graph, the different colors represent the time. So at the very beginning, the line is flat because it's at the beginning of the experiment. There is no movement, and little by little, you see that there are more movement in the right side, because it's where we are pushing the block, and you see that the movement is transmitted all along the fracture. Oops, doesn't move. Oof, I've lost my. Okay, I'm back. So the analysis of the experiment results is still a work in progress. So we are analyzing the first experimental campaign. So it presents itself like that, the DYC. We have separated the subject, the analyzed area, into 3 phases to in order to have the discontinuity of between the different block, and because it's what actually interests us. So what we are looking at is the average strain field of each phases, the displacement field in time, the displacement along both fracture, and of course we are also able to measure all the parameters that are possible to measure through classical tests, such as the normal and tangential stiffness of the fracture, maybe the fracture dilatancy, etc., which is a way for us also to validate the process. So to conclude, many research teams are working on the modelization of the drift of the underground research laboratory. We have chosen a new angle as compared to the other by working on viscous anisotropy, and by assuming that this viscous anisotropy is due to the fracture. So we can say that the first model allows us to reproduce the convergence by working on the anisotropic creep behavior. So we sort of validate the fact that the anisotropy of the viscous law has a major influences on the convergence of the drift. Then we improve the models by explicitly linking the anisotropy parameters to the fracture parameters. And finally, the objective will be completely achieved when we can feed the numerical simulation by zone with the experimental results and with our more detailed comprehension of the behavior of one fracture. So thank you for your attention. And do you have any questions?
Thank you very much, Sophie, for this interesting presentation. Now we have time for some questions. Does anyone have any question in the public? Okay, Philippe.
Hi, Sophie, can you hear me?
Yes, I can hear you.
I want to ask you, what kind of parameters do you intend to measure with your experiment for your models? What's the most important parameters that you don't have already?
The parameters is the viscous slip rate.
Okay.
Actually, we are willing to understand the slipping, the creep slip on the fracture with the hypothesis that I've made, or that I've already made for the homogenization. We assumed that the behavior was as Lemaitre creeps law. So if so, we would like to measure the parameter of Lemaitre creeps law, but actually there is no certainty that this assumption is true. So the first step is to just try to understand or see the behavior of a fracture, and then maybe identify the parameters of the law.
And the creep rate for the same rock, you already have this value?
Yes, I have experiment classical creep test made on Cox claystone provided by Andra, and I've already I've calibrated the parameter of my models on those tests. I can actually, I have the, oops, I have here. Yes, this was like creep tests provided by Andra, which I used to calibrate the parameters of the law of the Lemaitre creep.
Okay, thank you.
We have a question in the chat. Two questions. First one, what are the in situ stress? Is the depth fixed by the GOP or by geological conditions? Thanks.
So for the in situ stress, in the case of so the two drifts doesn't have the same stress, in situ stress. The first one, I thought I put it here. Yes, for the drift orientated along the major principal horizontal stress, the state of stress in a cross section is almost isotropic, with 12.7 MPa vertical and 12.4 MPa horizontal, and the major horizontal stress is at about 16 MPa of stress. So in the cross section of the other drift, you will have 12.7 MPa and 16 MPa in the horizontal direction. The other question was, the depth is fixed by the geological formation or by what? I can't.
Is the depth fixed by the GOV or by the geological conditions?
By the GOV is the government, I guess. Or no? Yes. Okay. So yes, it's the geological condition. They identified that Cox was a good host rock because of many different criteria, and the Cox is located at 500 meters depth.
Perfect. The second one, any reason for discontinuity in the disk displacement measurement? Can you reduce the effect of matrix deformation by shortening the sample?
Any reason for the discontinuity? Oh yes, there were a fracture. You cannot see it. Wait, I think the resolution is not good enough in the PowerPoint, but I'm in the wrong way, sorry. But here, no, here yes, the resolution is really not good, but maybe you can see it. I know that it's here, so I see it, but there is a fracture here. So it's the fracture closing that you can see on the, this explains the discontinuity in the displacement measurement. Okay. Reduce the effect of matrix deformation by shortening the sample. Maybe it's probably true. Well, I'm not sure. Maybe it should be tested, but then you have a less. I mean, we see that the behavior is heterogeneous along the fracture, and the sample is already quite short compared to the actual shear fracture present around the drift. So then we have to manage all the scale difference between the experiment of, not then, actually we have to manage the difference between the scale sample and the scale of the experiment and the scale of the fracture in situ, since we are willing to study the behavior of those fracture, of the in situ fracture.
Okay, so we have one last question. When you calibrate your strength parameters with this, is there any scale effect observed?
You mean in the experiment? I have not calibrate my strength parameters yet. So I believe that there will be some kind of scale effect, but I've not studied, I've not looked into it for the moment. But I can imagine that there is some scale effect, because as you can see it on the measurement, so the size is pretty much arbitrary. So of course it's different if I see only that, or if I see only those parts. I mean, and that's only half the sample, because as I said, we are taking two pictures, and that's only the results of one. It's only the results of the right side of the sample. So I don't know yet what happens on the other side. So probably there is a scale consideration to make.
One last question. Was it difficult to handle such, I imagine, big size photos according to the camera resolution?
Yes, it's difficult, but now it is difficult, but it's manageable, I think.
Okay, thank you very much, Sophie.
You're welcome.
Okay. Hello, everyone. If there are no more questions, let me introduce the next speaker of this webinar session. She is Alessandra Insana, a research assistant at Politecnico of Torino in Italy. She got her PhD in civil and environmental engineering in co-tutel with the Politecnico of Torino and the Université Paris-Est in 2020, with a thesis entitled Thermal and Structural of Energy Tunnel, for which she received the My Research in 3 Minutes Award in 2018 and was among the finalists of Prix Pierre Lande. Her current research activity are related to the study of the behavior of thermoactive tunnels, both for application to new tunnel projects, as in the case of Turin Metro Line 2, and for retrofitting of existing urban and motorway infrastructure. Today, she will present a talk entitled Challenges in the Lyon-Turin Base Tunnel Project. Alessandra, the screen is yours.
Thank you, Federico. So I will share the screen. Can you see it in presentation mode or not?
Yeah.
Okay.
Perfect.
Okay. So thank you very much for this kind introduction, and good evening, good morning. I don't know, based on where you are. So let me start this talk with this picture that I took a couple of weeks ago in Torino, but I will not unravel it now. I will leave the surprise for the end. Okay, let's see if I can go. Okay. And I have to, sorry, I have to move this. Okay, so we will see a brief introduction about the Lyon-Turin link. Then we will see two challenges as the title of the presentation. So the first one is the most obvious one, but also not for that less interesting, which is the issue of time-dependent behavior. So a very similar topic to the one that Sophie has dealt with. And we will see how to deal with it in terms of laboratory tests and numerical modeling. The second one is more visionary in a certain sense and more ambitious. So it's about opportunities from energy tunnels. And then there will be a brief summary. So before starting, a little bit of history. For those of you who are not European and not from France and Italy, so last year, we celebrated 150 years since the opening of the so-called Fréjus Tunnel. So you see a picture on the left. It was opened in 1871, and it was a tunnel that thought that transalpine tunnels were possible. It started with manual works, and then it went on with pneumatic drilling. So I taught a lot, but now it's getting a little bit old, and it doesn't comply anymore with regulations and standards, safety standards also, and also with current aims, which are to have a high-speed, high-capacity railway line, especially in the framework of the TEN-T network. This is why a new tunnel is being built at a much lower altitude. So you see here in this, maybe I have to, okay. So you see here the altitude of the new tunnel, the Mont-Cenis tunnel, much longer, so 57.5 kilometers against 13. And so I have to go on like this. No, sorry, I have some issues with automatic. Okay. You see in this picture the Trans-European Transport Network, and in green, this is the Mediterranean corridor, and I'm highlighting the Lyon-Turin link. The core of this link is, of course, this B-tube tunnel. We see a picture here, and during this presentation, we will focus on these two areas in the white squares. So the first area is that of the Saint-Martin-la-Porte access and survey tunnel, and the second area is at the border between France and Italy. So remember these two areas. So let's start with the first challenge, the time-dependent behavior. So as I said, we are focusing on this area. So we have 4 access adits, 3 on the French side and 1 on the Italian side. And especially in Saint-Martin-la-Porte, an access tunnel called SMP2 has been built between 2003 and 2010. However, this access tunnel crossed a formation called Carboniferous Formation Franc-Huillet, which is also the reason why here the tunnel had to be reoriented. So severe squeezing was encountered with the large metric convergences, ovalization of the section, and also failure of the preliminary support, of the temporary support. Now, since 2017, another tunnel, a survey tunnel called SMP4, is being excavated, still with conventional method, along the direction of the future southern tube of the base tunnel, and that will cross the same, that is crossing actually the same formation. So squeezing is expected. So how to deal with this behavior? Of course, there are in literature, empirical and semi-empirical relationships that allow to evaluate whether we can have squeezing or not, and also the degree of squeezing. But then we have to really quantify it. So in our laboratory, you see here some picture. We have this special equipment, which is called high pressure triaxial apparatus, that allows to perform triaxial tests at very high confining pressure. So you see here up to 64 MPa. It is fully controlled with automatic acquisition of data and also local measurements of strains in the radial and axial direction. So you see on the right some pictures during the setup of the specimen. This actually is a specimen of clay shales coming from central Italy. We have just concluded an experimental campaign on such material. And here you can see some examples of creep tests, triaxial creep tests that we have performed. So the creep curve corresponding to this deviatoric stress can be seen below. And we can also appreciate the so-called apparent consolidation phenomenon. That is that after a creep phase, when we reload the sample, the stiffness of the sample is much higher, but then it goes back to the stiffness it had before the creep test. Then another equipment is very simple, actually, and we used it because the other one was not available. And it's a mechanical frame, so very simple. We have a lower plate that is fixed and an upper plate that can move vertically thanks to a system of direct ways. And on this equipment, we performed an unconfined creep test that we'll see in a while, exactly on a sample of coal coming from SMP4 that I've described before. So once we identify that we can have creep, then the objective is to perform numerical modeling, so to find time-dependent constitutive laws that allow to well reproduce displacements, deformations, and stresses. Sophie talked about a time-dependent constitutive law for fractures. Here we're seeing the Shell-VIP model, which was formulated in 2009 by De Bernardi. This is an elastoviscoplastic constitutive model which couples the classical theory of elastoplasticity with the overstress theory of Perzina for elastoviscoplasticity. So the strain tensor is split into three components, so an elastic, plastic, and viscoplastic. So while the elastic and the plastic one can be strains can be evaluated as usual in the classical theory of elastoplasticity, the viscoplastic strain is based on Perzina's overstress theory. That is that we have, maybe you can see it better here. So we have a yield surface which the viscoplastic yield function can be both positive or negative. So if it is positive, then we can have viscoplastic strains, while if it is negative, we are in the elastic field, so we won't have any viscoplastic strains. So it's called overstress theory because it's a measure of the overstress, so the distance of the stress point from the yield surface. So the viscoplastic strain rate is expressed as a function of the so-called fluidity parameter, the viscous nucleus, the overstress function, and the viscoplastic potential function. The overstress function is assumed to be equal to the viscoplastic yield function. So the viscous nucleus is given by FVP to the power of n in the so-called Macaulay brackets, because so that if FVP is negative, the viscoplastic strain rate is equal to 0 because we're in the elastic domain. And the aspect of novelty of this model is the hardening rule. So the viscoplastic yield function is not fixed, but it can harden thanks to this rule. So in the triaxial stress space, we have two yield surfaces, the viscoplastic one, which is based on a linear Drucker-Prager criterion. So alpha P and Kp are the intercept and the slope with the Q axis, and a plastic surface sorry, I inverted them. So the plastic surface is the one that I've just said, and the viscoplastic yield function is homothetic. So the intercept with the p-axis is exactly the same, and the slope is given by alpha VP. So we can have three different behaviors: elastic if we are below FVP, elastic viscoplastic if we are between FP and FVP, or if we are exactly on FP, elastic viscoplastic and plastic. So this model is constituted by 11 parameters. 11 parameters. So 2 are elastic, 4 are plastic, and these ones can be evaluated according to classic triaxial, classic laboratory tests, for example, triaxial tests, and then 5 viscoplastic parameters. And then we have the state parameter alpha VP that defines the slope of the viscoplastic surface, so the onset of viscoplastic strains. Now we will focus on the viscoplastic parameters. This is important because then in the calibration procedure of these parameters, it's important to know their meaning. So gamma is the fluidity parameter, and it defines the amplitude of the viscoplastic strains. M is the shape factor, and it defines the shape of the creep curves. And we see here on the right that the value m equal to 1 is a kind of critical value, because if m is smaller than 1, then we can describe primary creep. If it is bigger than 1, the limit of the axial strain for time tending to infinite tends to infinite, so we can describe also secondary creep. And another interesting thing is that in the plane axial strain rate time, we have a long-term asymptote whose slope is equal to the inverse of m. Then we have n, the load factor, that defines the dependency of epsilon VP, the rate of the viscoplastic strain from the deviatoric stresses, a time stretching factor that scales the curve with time, and viscoplastic dilatancy, which is the ratio of volumetric to deviatoric viscoplastic strains. So in terms of geometrical effects of these parameters, if we increase m, the slope of the curves of the axial strain rate against time decreases. If we increase gamma, we have the curves move upwards, while if we increase L, then the curves will stretch towards the left. So if we look not anymore on the plane of the axial strain rate, but of axial strain, then the role of m is to change the shape of this curve. We've said it's called shape factor. Gamma, it changes the amplitude of the strains, and L changes the time scale. So you remember we have talked before about that mechanical laboratory testing, and for example, that mechanical frame. So on that mechanical frame, we performed unconfined creep tests with 5 loading stages. And we considered the first stage to illustrate the calibration of the parameters. So to calibrate the parameters, we didn't start from nothing, but we had some parameters that had already been calibrated by De Bernardi. So we considered, at the beginning, we considered exactly the same parameters, but we saw, now it's not very clear maybe, but we obtained the uppermost curve, so this one. So we had to change slightly the parameters to better fit the result from the creep curve obtained from the laboratory test. So in particular, what we changed was gamma, m, and L, but as you see, we didn't change them much. By the way, we have to remember that it's not easy to say we changed a lot or we changed little the parameters, because some expressions are to the power of m or to the power of n. Well, here n was kept the same, but m changed. So a little change in m might change a lot the other two, so gamma and L. However, we didn't change them much. But we have to say, before there was a question by Professor Aleana about scale effects. Well, here also we have scale effects. And so these parameters are not appropriate to simulate Then the in situ behavior, we'll see in a while what's the in situ case study that we have considered. This is due to heterogeneity of the rock mass, to the presence of joints, fractures, and of course to scale effects. So we moved to the in situ scale, and the case study that we considered is the case study described by Yi-Chun Liu in his PhD thesis. So we are focusing on changes between 10,310 and 10,410 in SMP4. So here basically till here, full phase excavation was adopted. Then at a certain point, there was a collapse of the face, and then also steel ribs were later destroyed. So excavation due to the presence of a fault. So excavation continued with excavation of a smaller tunnel, which is called PS, and then enlargement of this section to the so-called section RPS. So you see, well, here it reaches just 10,300, but since here, well, here also we enter the OUYE formation, so squeezing is expected. So we performed the 3D scale, 3D model using FLAC 3D. I didn't say before, we implemented Shellwhip in FLAC 3D, and we validated it against the triaxial test, creep test, and relaxation test. So we built this model, which is asymmetric, where the in situ stress is isotropic, it's 16.2 megapascal. And we reproduced the different stages of excavation of the PS and RPS tunnels. So you see below the stages. So first we have the excavation of PS, and we followed the stages followed in situ, so with a rate of 0.6 meters per day, then 12 meters behind the phase, the installation of the support, which is made by shotcrete and by the so-called ITCON elements, so high deformable concrete elements. And then after that, the excavation of RPS and 5 meters or 30 meters behind, depending on the chainage, the installation again of the same support. So as I said, the set of parameters found at the laboratory scale was not appropriate. So we had to change some parameters, and in particular, we kept constant N and omega VP because we believe that given the fact that N is related to the deviatoric stress and omega VP is the ratio of volumetric to deviatoric plastic strength, they can stay the same, but the shape factor, the time scale, and the fluidity parameter are parameters that may change in situ. So we had to recalibrate them. In particular, you see that M was assumed to be 2.2, while before it was smaller than 1. So it means that we're simulating also the secondary stage of creep. In this column, we have the parameters that also the Bernardi calibrated for the in situ case. And for example, we see that in his case, gamma was 8 to the power of -5, E minus 5. In our case, it's E minus 7. So it's smaller. This can be justified because in his case study simulated SMP2, and there the squeezing phenomenon reached the convergences of also 2 meters, while in our case we are at about 30 centimeters, so it's reasonable that this parameter is lower. So I have to say that this is still an ongoing work. We haven't found the perfect set of parameters that perfectly matches the behavior in situ. Now I'll show you. So here we have some screenshots taken when the phase is exactly in the middle of our model. So we are focusing the attention on chainage 10,344. Then when we complete the excavation and support of the PS tunnel, then when the phase reaches the same chainage for the RPS, and then when the excavation is completed here. So we see that the maximum displacement obtained is about 17, 18 centimeters. Indeed, if we, of course, these sections are extensively monitored, so we have the convergence data. So we see here the results of the monitoring. so the convergences in the direction highlighted here in the picture. And with the parameters that we have shown, the continuous curves are the ones obtained. So we are still underestimating a bit the convergences. Still, from the stress point of view, so here on top you see a picture of the stresses in these points measured in the shotcrete. So they reach up to 16.5 megapascal. We are in another change actually. And in the model, we are between 10 and 20 megapascal. So from the stress point of view, it works a bit better, but it's still ongoing work. So this was the first part. Then the second part, we said we focused on energy tunnels. So in this picture, we see the geothermal profile. So these triangles represent the temperature profile in that area that I highlighted at the beginning, at the border between Italy and France. So we see that the temperatures reached are quite high, so they are about 47 degrees. This is the tunnel elevation, and this is the profile of the Ambem Massif. So we have the tunnel is 2,000 meter deep. So we said, why don't we exploit this geothermal potential to extract thermal energy? So we focused the study on an area on a length of 10 kilometers. So we considered an average temperature in this area, which is also the area with the highest temperature, equal to 42 degrees. So the idea is to thermally activate the lining by using a net of pipes with a twofold aim. So the first aim is to cool the tunnel, because the request is to have a temperature that is lower, has to be lower than 32 degrees. On the other side, we could also profit from this energy that is extracted to fulfill energy needs in the area. So to evaluate the geothermal potential, we built a 3D numerical model coupled, so both thermal and hydraulic. So if we zoom on the tunnel, so we simulated the tunnel with its dimensions, so a diameter of 9 meters. And we also simulated the air explicitly with a finite element mesh, the air inside the tunnel, because we want to see the interaction between this technology and how the temperature changes inside the tunnel. So we defined the material properties, both thermal and hydraulic, in terms of thermal conductivity of the solid and fluid phase, the volumetric heat capacity, and hydraulic conductivity of the rock mass and of all the different materials. So as said, the boundary conditions are, in terms of temperature, are equal to 42 degrees. And we also have, we don't have a groundwater flow, but we have fractures that are saturated. So we impose a constant hydraulic head of 1,000 meters. And to take into account also the movement of the trains, sorry, the movement of the trains inside the tunnel, we considered an airflow of 8 meters per second and a heat source of 12 watt. The velocity imposed at the inlet and outlet of the pipes is 0.8 meters per second, and the inlet temperature is set to 24 degrees. So what can we see from the results in the long term? Well, here we have the specific thermal power, so thermal power per meter a long time. These are 10 years of numerical simulation. And we considered 4 different operating modes. So a continuous operating mode, a cyclic mode where the 3 summer months were excluded, or 5 in the third case, and a monthly activation. So we see that the thermal power that we can exploit ranges between 1.8 and 2.6 megawatts. While in terms of temperature, so of course, based on the operation mode, so the lowest value is for the continuous one. While in terms of temperature of the air, so inside the tunnel measured in this point, so here we see we have different behaviors. So with the monthly one, after 2.5 years, we are able to keep the temperature below the threshold. With the continuous one, we reach this aim immediately, while with the other ones, well, in one case, we reach this aim after exactly the end of the 10th year, while with the green curve, we still haven't reached 32 degrees. So these were 4 theoretical scenarios, but we have to say that the ideal operating mode depends on the aim. So if we want to provide continuously thermal energy, then we have to opt for the continuous mode. But if we want to ventilate the tunnel, then we could opt for the monthly activation. So it basically depends on the aim, and in any case, the use of the thermal energy lining has to be tuned to the aim, and we can have on and off cycles that are designed ad hoc depending on the aim. So here we see the results of our study at the top, and the results from a study by TELT in 2021, where they evaluated the thermal power obtained by using thermally the water drained during the excavation and bringing it to the portal. You see here to supply energy to the Susa Valley, so on the Italian side, for swimming pools, greenhouses, district heating. And the results that we obtained, so in the worst case, are very similar in terms of order of magnitudes to the ones that they obtained, and in some cases also more favorable. So it's a viable and interesting alternative. So to conclude, we have to say that when using time-dependent constitutive models, the calibration of constitutive parameters is not an easy task, and it's quite time-consuming. And we have seen that we have to do that both at the laboratory scale, and then once again, most often also at the in-situ scale. And for the future, an idea could be to try to relate, I think it's not easy, but to try to relate these constitutive parameters also to the proportion of coal or carboniferous shales, so that we could enhance the predictive capability of the constitutive model. While about the second topic, we have seen that the energy linings can be an interesting alternative, even because we have advantages, for example, in terms of ventilation of the tunnel. So that's all. Thanks for listening. Just a little remark. We wanted to invite you to the 16th IACMA conference that will be held in Torino at the end of August, beginning of September. The deadline for the submission of papers in a few days, but we can accept some very last minute abstract, and then let's see, for the papers, you can contact me very soon. And then, then I just wanted to reveal you what this picture is. So this is a monument in Piazza Statuto in Torino, and it's the Frejus monument, the Frejus fountain, and it is said that it is made by blocks, boulders that were extracted precisely from the Frejus tunnel, and these 7 statues represent the Titans. So it's the strength of the mountains that was defeated by the winged genius that is here at the top. So it's a science and reason that defeated brute force. So that's all, and thank you.
Thank you very much, Alessandra, for your very clear and interesting presentation. And now we have 10 minutes for the question and answer session. So are there any questions? Let me check in the chat. Yeah, there is a question from Ignacio. In the evaluation of thermal property of rock mass, did you account for the presence of fractures?
Okay, thank you, Ignacio. No, actually we didn't. So it's a very preliminary work, and so we kind of considered an equivalent, a sort of equivalent continuum model, but in the thermohydraulic domain, not mechanical. So we considered the thermal properties of intact rock. So thermal conductivity of the solid part is that of the intact rock. Probably the presence of fracture would also it would affect this, because it would decrease thermal conductivity slightly. So probably the thermal outputs that we have seen will probably be a little bit smaller. We do recognize this, and we are aware of this. So it's for sure something that we can explore more in the future, although we don't think it will affect that much the results. And thank you.
Okay, any other question? Philip Brown raised a hand. Philip?
Yes, thanks, Alessandra, for your presentation. I was wondering if when you model and when you investigate the properties of your rock, do you take into account the presence of water? Like, because often you can have like apparent viscous properties due to the water diffusion, and it's hard to distinguish the viscous properties of this diffusion and the one of the solid matter.
Thank you, Philippe, and hello. I took this case study from Yi-Chun Liu, and in his thesis he said that but you mean for the first part, right? Yeah, for the viscous part. So he said that there was no water there. However, I believe that if there was water, let's say that the constitutive parameters that we calibrate are homogenized, so they implicitly take into account everything, but implicitly. So it will be a result of the calibration, I mean.
So the water behavior will be included in the viscous.
Yeah, exactly, yeah.
Okay, thanks.
Thank you.
Are there any other questions? I have a question. How did you select the velocity and temperature boundary condition at the inlet of the pipe network in the second part of your talk?
Okay. I'll close this. Yes, because here I've said that we took these values and that's it. But actually, to select them, we performed some sensitivity analysis by varying the temperature between 20 and 28 degrees, and also by varying the velocity between 0.3 and 1 meters per second. So we saw that the thermal performance increases when the inlet temperature decreases, of course, and also with an increasing velocity. However, we didn't select exactly the combination that gave the maximum thermal performance, because we also counted for good practices in geothermal plants, that is not to have a very high difference between the temperature of the ground and the outlet temperature of the heat carrier fluid. So there's a magic rule that limits this difference to 17 degrees. So among all the combinations, we took the one that fulfilled this condition, and that also allowed to maximize the thermal output.
Okay, thank you.
Thank
Any
you.
other question? In the chat, no more question. Okay, thank you very much, Alessandra. I just share the screen and go to the end of this first ISRM Young Member Seminar. On behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. I would also like to thank Sophie and Alessandra for the very interesting and valuable presentation that address two relevant topics of rock mechanics. And we hope that this seminar provides you new insights, new challenges to research, and it could be a periodic event for sharing ideas about rock mechanics and related topics. And for this reason, we want to invite you for the next seminar that will be virtually hosted by Asia on February 23rd. Dr. Sho Ogata, assistant professor from Osaka University in Japan, and Dr. Seo Park, senior researcher at Deep Subsurface Research Center, Geological Environmental Division of the Korea Institute of Geoscience and Mineral Resources of the South Korea, will present their works respectively on development of coupled thermal, hydraulic, mechanical, chemical model for predicting rock permeability changes, and comprehensive in situ stress estimation for a fractured geothermal reservoir for drilling, hydraulic stimulation, and induced seismicity. Further information will be available on the ISRM newsletter and website. So keep in touch not to lose the next webinar. And if you are interested to participate or sending us your candidature for participate to this webinar, write an email to the email address in the slide. So thank you for your participation, and have a good and safe day. Bye.
Thank you. Bye.